Hello, my name is Jeremy McNew, Grantham Student ID G00136516, and I am presenting the Automated Livestock Feeder ET450 Capstone Project. This presentation covers a narrative of the concepts, design, construction, and operation of the feeder, as well as a demonstration of its use. I'm here on a small hobby farm where the idea for the automated livestock feeder was first conceived. The problem was the owners would go out of town or on vacation and ask for help from their friends and neighbors to get the animals fed while they were gone. When they came back, they noticed that their animals had either been overfed or underfed, and at irregular and inconsistent intervals. This can cause health problems for the animal, as well as wasted feed and additional costs for the owner. The idea was to design and build a product that could be operated at the push of a button and deliver a consistent amount of feed at every operation. The device needed to be able to store the feed and protect it from the weather, the elements, and other pests. It needed to contain some sort of drive mechanism to convey the feed from the container into the feed bucket for the animal. And it needed a control device to activate the delivery system. The product also needed to be scalable so as to be able to provide feed to a range of different animals, such as chickens, sheep, horses, and even cats. The engineering aspects of this project were broken out into three phases: the design, the software, and the hardware. The idea was that feed would pour out from the storage container above through a hopper into the drive mechanism. It would then be pushed out by an auger controlled by a servo motor up this tube and out this spout into the feed container. The servo is activated by the control circuit at the base of the unit.
The circuit is controlled by an Arduino microcontroller powered by a 5-volt external power supply. Attached to the controller is a power switch, a continuous rotating servo, an LED, a push button to activate the code, and some resistors. A standard red LED needs about 1.8 volts to operate, but the Arduino provides 4.8 volts from its digital pins. A 100 ohm resistor in series is more than adequate to alleviate this while keeping the LED bright and allowing for tolerance. The activation button is comprised of a pull-down circuit that holds the voltage on the input pin to a low state. Once pressed, the high resistance directs the voltage to the input pin, putting it at a high state. Here, a resistor of 10,000 ohms or more is sufficient. Lastly, the servo needs a ground and a 5-volt power source. It activates when it receives a voltage on this control line. Once this line deactivates, the servo will hold its position until reactivated.
The software for this design is pretty straightforward. The controller needed to provide output to the servo motor and the LED while receiving input from the push button for activation.
I first established my pin variables for use in the code. I also needed a variable to keep track of the state the push button was in, as well as an object to control the servo motor. I then attached the servo object to the servo pin and defined the pins as inputs and outputs. The operational part of the code begins with determining the state of the push button and assigning it to the push button variable. If it has not been pushed, the feeder just sits there. But if it has been pushed, the servo and the LED variables both get set to a high state. There is a delay of 30 seconds before the servo gets deactivated, followed by a small delay before the LED gets deactivated.
The hardware engineering phase of this project proved to be the most difficult. I began by recreating the circuit that we had simulated in Tinkercad onto a breadboard. Once I could get the push button, the LED, and the servo motor all functioning correctly, I then integrated the controller circuit with the screw conveyor assembly. Once the screw conveyor subassembly was joined to the controller circuit, we began testing the amount of time needed to deliver 1 cup of feed through the tube. The initial plan was to test this at 45 degrees. However, this elevation required approximately 127 seconds to deliver the full amount of feed up the tube. We decided this was too inefficient for the feeder to function properly. We then decreased the elevation to 10 degrees and measured the time at just under 30 seconds, followed by 20 degrees, which was approximately 48 seconds, and 30 degrees, which was approximately 97 seconds. We went back down to the 10-degree range and tested up to 15 degrees to get an accurate reading and settled on 12 degrees at 30 seconds. This resulted in modifications to the length of the tube and the use of the elbows of the PVC pipe. The next step was to find a way to get the feed to flow into the hopper. The original design called for a small inlet in which the feed would pour in. However, this proved to be also too difficult as the feed would become clogged in the screw conveyor. We began experimenting with various types of funnels, measuring the flow rate that the feed would pour out due to gravity. I tried multiple designs of a pyramid, a cone, and a sphere, and had varying results with each. Ultimately, the cone gave me the best results as long as the diameter was sufficient enough for the feed to pour through.
With the funnel printed and attached to the hopper, along with the screw conveyor subassembly, the microcontroller circuit, and the controller interface buttons, I then tested the operations of the feeder at near full assembly. This gave me the opportunity to troubleshoot the system as needed without the tray installed and still have full access to the screw conveyor and controller circuit. As you can see, the feeder performed exceptionally well, moving a full cup of feed out of the feeder into a measuring cup in just 30 seconds.
The final step was fabricating a tray out of aluminum sheets to store the feed above the funnel. This was attached to the inside of the storage container with pop rivets. The device was now ready for a full systems test. So we're back out in the barn where the fully functional systems test, and I got my special assistant Daniel who's going to give me a hand. All right, Daniel, are you ready to test?
Yep.
Okay, step 1, remove the lid.
Passed.
Step 2, add feed to the feeder.
Passed.
Step 3, replace the lid.
Passed.
Step 4, power on the feeder.
Passed.
Step 5, activate the feeder.
Passed.
Step 6, power down the feeder. Step 7, call the dog and make sure you pick up that red bucket. We don't need it from that.
Chief! 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 Come on, Chief! Come on.
Well, is it a pass?
Pass.
This concludes the operations demonstration of the automated livestock feeder ET450 Capstone Project. I hope you have found this presentation both informative and beneficial. Thank you.